just like earlier we had a vector multiplied by a scalar, it would be similar to this del operator acting on a scalar, and this is known as the gradient. If we, in analogy with the dot product, write A dot B, similar to that we can write del dot a vector quantity V. That means this operator will operate on V. So, this kind of operation is known as divergence. And similar to cross product A cross B of two vectors, we can write del cross V, any vector quantity, and this operation, again it is not a cross product, it is known as curl. Now, let us define the divergence first. The divergence operator del dot V, it operates quite similar to the notion of dot product. So, I am first writing the del operator x cap del del x plus y cap del del y plus z cap del del z, and that will operate on x cap Vx plus y cap Vy plus z cap Vz. And if we perform dot product, we will get del del x of Vx plus del del y of Vy plus del del z of Vz. So, this is exactly the operation. That means, we perform this divergence operation on a vector field, that is V in this context. We have three components, three Cartesian components of this vector V, and after operating we get a scalar as the output. What does it geometrically mean? So, geometrically divergence would mean if we consider a point and there is a vector field around it that goes somewhat like this. Here I am showing a vector field that diverges from a point. In this kind of a situation, we would say that at the point the vector field has a positive divergence. That means, the vector field is diverging from this point. If we have the arrows pointing towards that point, that means the vector field is converging to that point, then the divergence of the vector field at that point would be negative. And if we have a situation where the vector field does not change at a certain point, it does not diverge, it neither diverges nor converges. In that situation, we can say that the divergence of the field there is 0. If we have this kind of a field, the divergence would be 0. And let us consider another situation where we have the magnitude of the vector is increasing as we are moving upward. There can be this kind of a situation. So, let us call this the leftmost case as situation A, the middle one as situation B, and the rightmost one is situation C. And let's see how we can calculate the divergences. So, for case A, okay. For case A, this is similar to the position vector. So, here the vector in question can be written as the position vector, which is nothing but x cap plus y cap plus z cap in Cartesian coordinate system. And if we calculate the divergence of it, we will see that this quantity would be x cap del x plus y cap del y plus z cap del z dot x cap plus y cap plus z cap, and that will give us del x plus del y plus del z, which is 3. We get 1 from each of these derivatives, and finally we get 3 as a result of it. So, we can see that the divergence for this kind of a vector is positive. The situation B, case B in this picture is nothing but it's same, the magnitude of this vector is constant and it's pointing upward, that is along the z direction. So, for case B we can write it in the following way. The vector field can be described by this equation, any constant A multiplied by z cap. And now, if we take the divergence of this quantity, divergence V is given as x cap del x plus y cap del y plus z cap del z a z cap. So, only the z component survives, that means we have del z of a constant which gives us 0. So, this vector neither diverges nor converges. Let us come to case C. Case C is where we have the magnitude of the vector is increasing as we move higher along the z direction. So, this vector field can be represented as this V equals z cap, that is what we intend, or any proportionality constant can also be there, but that does not matter. That is not going to give any qualitative change in the picture. So, the divergence of this vector V can be written as x cap. So, the del operator first, this del operator operated on z cap. Only the z component will survive, everything else will go to 0 as according to the rule of the dot product, and we will be left with del z, that is 1. So, we have a positive divergence of this vector field at any point in the field. That is something we can clearly see from here. And this example also clarifies the physical meaning of divergence.